Hey everybody. So this is your week 10 wrap-up video on unsaturated compounds. So let's get started. All right. All right, so a lot of you were having questions about the geometric isomers and the cis and trans. And I do want to kind of preface and say that remember, you are doing general, organic, and biological chemistry all in one semester. Most science majors, chemists would do that in 3 years. So, unfortunately, we don't get into some of the deeper topics. Because this course is asynchronous, I actually think you guys are getting more content, more time with the content than when I have this class in person and we're in lecture and sometimes we go over topics very quickly. So it's like cis and trans is something we touch on really briefly, but with the videos and the content online, you can watch those as many times as you want and then bring any questions you still have to office hours, which I kind of think is cool. Okay, so what I like to do with cis and trans, this is how I like to approach them, is I look at the double bond and I like to draw a dotted line where the double bond is going. And then I look at, again, you're not comparing, like on this left, you're not comparing the up to the bottom, you're comparing what's attached to these carbons, okay? So for instance, we have this methyl group right here and a hydrogen. And the highest priority group out of these two is the methyl group, okay? And then again, over here, the methyl group. So these two methyl groups, they're on the same side of this blue dotted line. Therefore, for the isomer, they're considered a cis isomer, okay? Now this one, again, imagine a line or draw it out if you need to, where the double bond goes. And then again, I'm looking at those methyl groups, and this time I can see that they are on opposite sides of that double bond. And so that is referred to as trans. Okay, so here's a couple more. Sorry, it's a little blurry, but this is up here is what we just saw. If we look at something like this, sometimes those the line drawings can be a little bit hard, but if imagine I could draw a double line right here. I'm sorry, a dotted line right there. In fact, I can't, well, imagine I can draw a double line right here, okay? And if I did that, I would see that I have this big ethyl group up here and this methyl group right here. And I'm assuming there's hydrogens here that are not being shown. But notice the groups that had priority are on the same side of that line. So this is cis. Again, this one, if I drew a dotted line across this where the double bond is, I can see the ethyl group here and then the methyl group on this other side. And I can see that this is trans. They're on opposite sides of that double bond. It also comes up in ring structures. So let's see, let's get this thing to go away. Okay, so with ring structures, you can see here both the methyl groups on the same side of the ring right here. And so that is cis. And then over here, we have a methyl group above the ring. And down here, we have a methyl group below the ring. I apologize, guys. Go away. Oh my gosh. Okay. And so this would be trans and this would be cis. If you have something like a halogen, they would take higher precedence than the methyl groups. So again, if you imagine a line here, these bromines are going to be the higher priority. So this is a cis isomer. This time the bromines are on opposite side of this dashed line. So this is a trans. And the way we show that, some of you have asked me about the wedges and the dashed triangles. And that's what's shown in this bottom right corner. If I have two wedges, that means they're both coming out at me. So like above the plane of whatever I'm looking at, whether that's my computer screen or my paper. And so this is a cis. Here I have one solid wedge and one dashed wedge. So the dash wedge is going away from me. So like into the past, the plane of the paper. So like into my computer screen or into my desk, whatever surface. So here I have one chloral group above the plane of the ring and one below the plane. So this would be trans. Okay, so the question Oh, well, I guess there wasn't a specific question, but again, a lot of you were asking for a little bit more information on cis and trans isomers. Okay, so then the properties. So basically, when it comes to properties of all the organic groups we'll look at, we want to know basically kind of what's the trend and its boiling point. If we can kind of, and then is it soluble in water? Okay. Now, if we look at the atoms present in the molecule and what they're attached to, we can kind of deduce this instead of memorizing it. But I'll leave that to you. You decide how you want to handle the material. So in things like alkenes, all we have are carbons and hydrogens. They're double bonds, but that's still carbons and hydrogens. And we know the only intermolecular force, again, this is from our general chemistry segment, remember, is London dispersion forces. And these are relatively weak. Remember, there's London dispersion forces, dipole-dipole interactions, and then a stronger form of dipole-dipole is a hydrogen bonding, and then ionic bonding. Okay, so London dispersion is like the weakest intermolecular interaction. So we can see that we have boiling points here on the y-axis, number of carbons on the x-axis. So with and alkenes are shown in the purple square here. So with 2 carbons, we're at minus 100 degrees Celsius. As we increase the number of carbons, we can see our boiling point does increase, okay? Since it's all carbons and hydrogens, these are not polar bonds, it's a non-polar molecule, therefore it's soluble in non-polar solvents, okay? And insoluble in water, it doesn't dissolve in water. So one of the questions was, which is a good solvent for cyclohexene? So 6-membered ring, double bond. Would it be pentane or water? Okay. So like I said, if you can think of cyclohexene, okay, all carbons, all hydrogens, all non-polar bonds, therefore only soluble in a non-polar solvent. So water would not be a good choice. So pentene is going to be the choice here. So again, to summarize real quick, physical properties of alkenes, they have relatively low boiling points, but their boiling points do increase with size, and they're insoluble in water. Okay. All right. And no one really asked questions about this one, but in our content on Top Hat, we looked at the hydration of alkenes, but alkenes can undergo all these types of addition reactions. I don't expect you to know them all. I expect you to know the hydration mainly. Hydrogenation is also important. Notice this says hydrogen. It's adding hydrogen across the double bond and you get an alkane, okay? Hydration, like think of dehydration. Hydration has to do with water. So this is adding water across a double bond and you add a hydrogen to one carbon and an OH to the other. And so there was Markovnikov's rule that says the OH will go to the carbon with less hydrogens. Easier to remember is that the hydrogen will go to the carbon that has more hydrogen, okay? And then the same thing, bromine can add across a double bond, and then you can get a hydrohalogenation, meaning you have H and some halogen, so bromine, chlorine, and again, one carbon gets the H, one carbon gets the chlorine. Ooh, a lot of you guys were asking about polymerization. We'll get more to polymerization, when we start getting into the biochemistry, the biological chemistry part of this course. But basically, in any kind of polymerization, you have some monomeric unit, which is like the small unit, and then the polymer is a bunch of these monomers stuck together. So real classic example is like in proteins, right? You have amino acids are the monomeric unit, the smaller unit, but then you have a bunch of amino acids connected together and you get a protein, okay? DNA is another example. DNA is made up of nucleotides, the A, C, G's, and T's, and those are the monomeric units. You have a bunch of those connected, and that creates your nucleic acid, your DNA, okay? And so here, our monomeric unit, one of the examples you had was just an alkene, right? This is ethene. And we can take a bunch of ethenes and they can stick together and form a polymer. And you can think about it in this double bond, right? 2 electrons make up a bond. So you have 4 electrons here. You can think that the electrons of one of these bonds breaks and then forms a bond between this carbon and its neighboring carbon. It forms a new bond here. And then again, one of these bonds breaks and forms a bond between this carbon and this carbon here. And then this bond breaks and it forms a carbon between this one and the next one, and so on. And so you get this really, really long, and again, the number of monomeric units is usually not specified because it's just so many. But that's what a polymer is. You get like this long chain of these monomeric units put together one after the other. Okay, aromatic compounds. Oh, that was fun, huh? So the thing with aromatic compounds is sometimes they're represented like this benzene molecule right here in the middle, where you have alternating double single bonds. And so students might automatically think alkene. But when you have it like this, where the double bonds are alternating, it has some special properties that are much different than alkenes, okay? And so, and then this can be represented like this, but you could also easily represent it here, where this was once a double bond, now it's a single bond, okay? So they're alternating single and double bonds. So we can take these two structures and represent it like this with this dashed line in the middle, or you've seen it a lot like this on Top Hat where there's just a circle in the middle. So these are all represent the same thing, an aromatic compound. They all represent benzene, which has C6H6 for its molecular formula. And so let me just see. Okay, so with the main difference with aromatic compounds and alkenes is they don't undergo all those addition reactions we just saw with the water, with the hydrogen, with the halogens. They are more stable because these electrons of these alternating double bonds just kind of delocalize over all the carbons here. So they're not really reactive, okay? So aromatics tend to be more stable than alkenes. So don't assume when you see an aromatic compound, it's gonna undergo the same chemistry as other alkenes that we've seen. So for naming the aromatic compounds, there's IUPAC and traditional. So something about naming is that, again, as we go through this course, naming can get complicated really fast. So we're keeping it relatively simple and straightforward for this class. And maybe you guys don't feel like that's the way it is, but again, we just want to do the basics of the naming, okay? So here we have an ethyl group connected to a benzene ring. So it's just ethylbenzene, okay? This chlorine connected to a benzene ring is chlorobenzene. There's some traditional names that you should be aware of that are used a lot in aromatic compounds. So this benzene ring attached to a methyl group is commonly referred to as toluene. And then this benzene group attached to this amine, this NH2, is aniline, okay? If a benzene ring is acting like a substituent, so notice that this is a 10 carbon long chain, so it's going to take a higher precedence. So this becomes a substituent, and when that's the case, this is known as a phenyl group. So this becomes 2-phenyldecane, okay? Here, again, we want to give our substituents the smallest number, so this is 2-methyl 3-phenyl octane. So when benzene is a substituent, it's referred to as phenyl. And then you guys should be kind of familiar. I thought this was pretty straightforward, but in case on these rings, if you have two substituents and they're right next to each other, you can refer to them, again, this could be 2-bromotoluene or simply ortho. And for short, it'll just be O-bromotoluene. Here, we're going to give the lower number to the halogen that comes first alphabetically. So bromine will be 1, chloro will be 4. Here they're on opposite ends of the ring. So that's para, and we abbreviate that with just a P. This is 1-bromo-4-chlorobenzene, or P-bromochlorobenzene. And if they're not exactly opposite, but right next to each other, so that middle position, that's called meta. So this is 1,3-dichlorobenzene. Okay, so our M-dichlorobenzene, okay? And when we have multiple substituents on a ring, we wanna make sure we give them the lowest numbers possible. So this is 1, 2, 4. trichlorobenzene. And then here, this is, we want to put the bromine first because it comes first alphabetically. So this is 4-bromo-3-chlorotoluene. So this is one of the ones you guys said you had a trouble with. Oops, sorry. And again, the benzene ring with the methyl group on it is toluene. And so that's going to be assumed to be carbon 1. And so again, so remember, if they're next to each other, like here, then that's referred to as ortho. Okay. So like ethyl, there's no ethyl group here, so you can eliminate that first option. Isopropyl, there's no isopropyl group, so you can eliminate that option. O-bromotoluene, remember toluene is benzene ring with a methyl group on it. O tells us that it's next to the methyl group, and that's how it is in our structure. So that would be the right answer. And this is dichlorotoluene. There's no chloro groups here. Okay, so that's that. Okay, I think that's all the questions from week 10. So I hope you guys are all enjoying your and all enjoying the course and all the material. And please take care of yourselves. You guys, if you guys can like the comments that you want me to address, I do not have time. I'm getting like 1,000 comments a week, so I can't go through them all. So I sort, and the most like are what I look at, the top ones. And so that is what I'm going to address in the videos. And if you guys can articulate your issues a little better, then I can maybe address them better too. So sometimes it's just like, oh, this is confusing, you know, or when you guys, so again, I tend to address the ones that like, I don't understand the third question, then I'll put it in the video. Or if there's something really specific. So just try to articulate what is kind of confusing. And I highly encourage you guys to come to office hours if you can. You have me Thursdays 10 to 11 or 2 to 3, Dr. Sherritt Wednesdays 10:30 to 11:30, and Fridays 11:30 to 12:30, and Dr. Farmers on Mondays from 4 to 5, I believe. Okay, it's all on our Canvas page. And again, there's tutoring through Mesa, there's drop-in tutoring, and you can schedule with them. So you can do either one with Mesa. And there's Lark that has scheduled one-on-one tutoring. So take advantage of those options that are available to you. And again, work the problems. Just watching videos is not going to cut it for this class. You need to work the problems. Again, if you need to do it with a tutor and then on your own, you know, either way. So that's really important. Okay. I hope you are all healthy and safe as always. And just please continue to take care of yourself and check in with yourself. All righty.